last time. You right? So Christopher's from Brisbane, and he is an IoT expert, I would describe him as. He's the convener of the Brisbane IoT Internet Group. He also has a consulting firm doing IoT work. He has a huge interest in electronics. He's shared a lot of really interesting hardware and software projects at LCA before. What he's talking about today is an LED Christmas star, which he made and designed in an afternoon, had the circuit boards produced custom, and he's going to walk us through the process of how he made that project, and then take that a bit further and looking at PCB, rapid PCB design tools, and how everybody can make the most of these opportunities to not just wire hardware and software together, but actually design the physical units to kind of reflect the kind of purpose that you want to put them to, and how we can turn that into a creative art form. So let's give a round of applause for Christopher.
All right. Let's see how we're going here. Oh. Lovely, we're moving. G'day, so my name's Chris, and today I want to tell you about the things that I do on the intersection of technology and art, and how hopefully I can convince you that you can do this too, that it's not as frightening as you thought. So I'm not an electronics engineer by training. I'm a computer programmer, but I have been involved with electronic gadgets since I was a teenager, and as a hobby throughout 20 odd years as a software engineer and manager. And a few years ago I decided to take that passion full time. And so now in my day job I operate a business called Accelerando, which helps businesses use technology to reduce stress. Because really that's what I believe, that technology is the gradual process of freeing the human race from drudgery and fear. And so I started my business because I wanted to contribute to the kind of future that I would be excited to live in. At the last LCA, I talked about rapid manufacturing techniques such as 3D printing and laser cutting. And I touched briefly on electronics in that talk, but I didn't really have time to go into much detail. So here we are, it only took a year. But first, I want to talk about why I want to talk about what I want to talk about. Did you follow that? There's a lot of confusion about what the Internet of Things really means as a sector and as a movement. Like any new buzzword, there's a lot of piling on by existing players who simply want to siphon off mindshare from a new technology. But what the Internet of Things means for me is using low-cost computers and the communications between large numbers of them to improve our lives, which dovetails neatly into my approach to art. There's a perception that technical folks are not arty, but in reality, there's a huge movement and subculture among technical people of creative arts. I think it stems from the fact that technical people spend a lot of time working on abstract concepts or working on things that are literally behind the walls. And so when you're at that Christmas barbecue or at the pub and somebody says, well, what do you do? It's very difficult to show people what you do. So having art is a fabulous release for technologists in being able to demonstrate something that I made, which is not always to say that our creative outputs go in the wrong way. Now, it's undeniable that people are creative. It's perhaps debatable as to whether some of the things we create are a good idea. This is a television from the 1930s. And the reason I'm showing it to you is I want to tell you about what life was like before the technologies we have today. This is a bunch of electronic components that are simply all wired together. Maybe they're stuck to a bit of cardboard or Bakelite, and then they're wired up. And each television was an individual work of construction. And as electronics moved into taking over our lives, this became very much a brake on the kind of things that we could do. And so experimentally in the 20s and 30s, but then increasingly in the 1940s, 50s, we started using different technologies to put together our electronics. And in general, I think that technology is the art of thinking about a better way of living our lives and building our society. So the better way from that mess inside the 1930s TV cabinet is what we call the printed circuit board. And the idea is that you've got a sheet of fiberglass, you've got a thin sheet of copper rolled onto the side, and then somehow you get rid of the copper that you don't want in order to replace all those wires with a single set of connections that are permanently fixed onto that piece of fiberglass. Now, this is one that I actually made in my kitchen, and I'll be recommending that you don't do this because it's easy, it's relatively cheap, it's not particularly dangerous, but we're at the point now where the commercial services that will do this for you are so painless and quick, and their quality is so good that the number of ways that we used to do this in the home or the small workshop are very much becoming obsolete. And this is what the front of that board looks like. This is a system that I made to try and head my children off from their tendency to get up in the middle of the night, turn on every light in the house on the way to the bathroom, and then go straight back to bed and leave them all on. So this controls, with a motion sensor, the lighting in the bathroom and flips it on. And it's been sitting in my bathroom for about 15 years now, and it's still ticking along. But the general illustration here is that you have a bunch of electronic components that you stick through a board, and then they're soldered on the backside. And this is how practically everything that we interact with that is electronic is made today. And the interesting thing is that some of our most commonly used appliances, like televisions, DVD players and such like, are not using techniques that are much more complicated than this. Our computers, our phones especially, are using many, many generations ahead of this. But it's interesting to me that a lot of technological niches are really quite conservative in that they're using techniques that arose half a century ago and they haven't changed them. And so today I'm going to talk to you about a number of tools that you can use to get from a jumble of wires to something that is robust and able to be reproduced and will survive the journey in your suitcase from A to B. And this is a program called Fritzing, which is a tool for guiding you through that process from jumble of wires to finished product. And this is not unlike what Jacob just shows us. Is a small device for making music, and that's what you might come up with if you had a bunch of parts on your workbench and you just wire them together to see what you could do. And the next step is to turn that into what we call a schematic diagram, to say, okay, I've got this part, I've got that part, it's hooked up like this. And then we want to make a printed circuit. And up until perhaps the late 1980s, this was done by engineers who would sit there with a pen and paper or a roll of little black tape, and they would manually design that conversion from jumble of wires to printed circuit. Nowadays, we have software that does it for us. So we merely need to say, okay, I want to put this switch here and that plug there, wire it up for me. And you might think, I can't do that. That's way too complicated. I don't understand anything about what's happening here. But what I want to tell you today is that you can, and it's not that scary. So meet the most successful robot ever, the Roomba. It's not actually very good. It doesn't do much more than drive around and bump into things. but the important thing that it does is it does a job that we particularly don't want to do well enough to carve itself a niche. And before I go further, I want to rewind it a little bit and look back at how we got here. And artists had a lot more to do with this than you might think. Ooh, we got a glitch on the slides there. After the Second World War, we started using electronics to control a lot of our lives. And this is before the computer, as far as most of us knew, because computers at the time were a military secret. And so these devices came along called the programmable logic controller, which essentially were the encapsulation of a bunch of switches and timers. If you've ever fiddled with a washing machine where you have that big clicky dial that you have to turn to get your spin cycle or whatever, this is the kind of technology that the industrial world still uses today. It's remarkably non-technical. So let's fast forward to the early 21st century. This is a device called the Arduino, which many of you might have heard of. It was really the watershed in technology where it became possible for someone who is not an electrical engineer to automate things, to make blinky lights, musical instruments, what have you. And there was actually a huge amount of resistance to this from electrical engineers. It was asking for a flame war to even talk about this product on electrical engineering forums, because they dismissed it out of hand. This is pointless, this is junk, this is too simple, nobody will like this. And what a lot of people don't know, that this was invented by artists. A couple of university lecturers in a pub in Italy sat down and looked at, why is it so hard for our art students to produce electronic art? And the reason is that the technology that was there for automation, designed and built by engineers, conservatively so in that it hadn't changed significantly for decades. And so these people looked at what could we do to make electronics a friendly workspace. And so fast forwarding from there, the Arduino came along around 2005. Over the next 10 years, they got smaller and faster, more processors, more memory. And then Wi-Fi comes along. So now we're at a situation where for $5 you can buy a little circuit board that's got a brain, some memory, perhaps a screen like this one, and you can talk to it over the network and do all sorts of interesting stuff with it. And this is what I think of as the current sweet spot in do-it-yourself electronic installations. It's a little board called the Lolin D1. And the good thing about this is there is no wiring. If you want to build something, you just stack them together. I want a switch, I want a screen, I want a speaker, I want some lights. Grab a bunch of modules, they cost $1 or $2 each, stack them together. And there's a useful agglomeration. It doesn't actually look very pretty, and I'll talk a bit more about that later. But here we are, living in the future, and I really mean that. I think a lot about where technology has brought us and what it might bring for us in the future. I see a lot of electronic scooters around the campus here, and if you invert the progress of history and look at what are the things that we have now, imagine a startup came along and said, we've got this new device, we're going to call it the automobile, and you just buy one and then you leave it wherever you want around the city for the day, and then you come back to it when you're finished. It sounds crazy. So thinking about the context of technology is the important thing for us to do. And so what I want to do now is use some of the projects that I've done in the last year to illustrate the journey from concept to installation. And also I want to give you some tips about things to think about when you're building electronic installations. So here's a gadget that I built, again, out of the necessity of improving my children's lives, because they are essentially small biological machines for losing house keys. So they come home from school and I get a text message saying, "Dad, I locked myself out again." So I built a system where they can open the front door from their phones. It's not pretty. It's a stack of those D1 modules that talks to a electronic door latch. And so I found myself wiring up the same little gadget over and over again for a couple of door installations around the house and around my office. So I thought, okay, well, obviously here's a component that I need to build. So I designed and built a module that fits on that stack that does the particular thing I need to talk to that door latch. And one of the things I want to point out about this is going back to today's keynote, the documentation. All the connections about how to use it, about what it does, where to get the instructions even, are printed on the circuit board as part of the manufacturing process. But that's still a bit messy, that stack of boards. So let's think about neatening things up. And the good thing for us as non-specialist electronic dabblers is that there's a huge variety of inexpensive little modules that we can glom together to do our job. So these are essentially the processor and memory and Wi-Fi out of one of those D1 boards, stuck under a little module. That's an Australian 5-cent piece there. So we're looking at a module that's maybe 8 or 10 millimeters across. And what this allows us to do is to build remarkably complex stuff from simple parts. Now this next one's probably going to frighten you, but this is something that we built to help a client who was building sensors that they were going to put under the road, where they literally drill a hole in the asphalt and drop it in there and concrete it in. And the problem with that is if you stuff it up, it's backhoe time to go and fix it. So they wanted a way to turn these things off and reboot them should they go berserk. And so we built this little system which just does that one thing. It allows you to talk to it over Wi-Fi and control a relay. And it's really just two of those little pluggable modules stick together. You've got a brain, you've got a relay, you've got some lights for helping you understand what it's doing. And this is something that was designed by one of my team who'd never built a commercial circuit board before. He sat down and in the course of a couple of days went from, okay, here's our prototype bundle of wires to here's something that we can build a few dozen of and try them out in the field. And if you're wondering what you can do with the little Raspberry Pi board that came in your swag bag if you were lucky enough to get one, then our next iteration of that product got a little bit more complex. We designed something that would clip onto the top of a Raspberry Pi. So the Raspberry Pi does all the thinking. That's a single board computer that's approximately as powerful as a cellular phone from a few years ago, which is to say approximately as powerful as a supercomputer from a decade ago. And one of the things I want to point out to you as a possibility is that you're not limited to the rectangle. So in this case, we had some switches, we had some connections to batteries and to outside things that we were powering, and we built the circuit board to carry all that design along with it so that there was only one way to put it together. And we also incorporated the lights which tell you what it's doing that would become the control panel onto the circuit board. So when you're designing a circuit board, you have the ability to think about the physical form factor of what you're going to do and shape it however you want to make it as simple as possible. So next step up the complexity chain, perhaps to the extreme, looks a little more complex, but again, not really. It's again our little Wi-Fi module. It's got a radio module for long distance, low power communications. And all it does is listens to your water meter and transmits its little blips that it makes every time the needle goes around up to the internet, which lets multi-tenant dwellings understand the water usage of their tenancies and such things without having to go and replace all their metering with smart metering. And again, this was something that we prototyped as a bunch of wiring. We built a dozen or so of them to do field trials, and the complexity is really just at the level of plugging Lego blocks together. Now this is something that is far more complicated. This is an evolution of our road traffic underground control system. But the reason I'm showing you this is to point out that even this, which is far, far beyond my capabilities, was designed by one of my interns who's an undergraduate. So there is a long way that a non-specialist can get with modern tools. It did take us a couple of revisions to get this right, and one of the things I want to suggest to you is that if you're getting printed circuit boards made, the colour is largely irrelevant, except that if you make version 1 yellow and version 2 green and version 3 pink and version 4 white, you don't get them mixed up so much. Another thing that's really helpful is touchscreens are dirt cheap. So nowadays you can get one for well under $10, which means that having to listen to beeps to figure out why something's not working, or that horrible experience where you're trying to set the clock on your car and you have to hold the button down for 5 seconds, wait till it flashes and then push it again, and if you stuff it up you have to go back to the beginning. That's one of the things that we really ought to consign to the bin of history, because we're now at the point where everything can have a screen for basically no extra cost. Bonus tip, again, from this design, and I don't expect that any of us will be building things this complicated, but there's little screw holes on each corner of that board, and they're actually mounted onto the circuit board as if they were soldered on components. So it's not just electrical components that we can put onto these assemblies. We can put screws. This one's got fuses. This one's got connectors. This one's actually got other circuit boards which plug in that are replaceable. Should it be struck by lightning, we can rip that part out and replace it with another one. So those are the kinds of things that you can do to turn your jumble of components and wiring into something that's more robust. So I want to go through now a quick journey from sketchbook idea to final product to show you again how the tools help us do that quite simply. So I was asked to come up with a display for an aircraft hangar that would tell people the outside wind speed. They've got anemometers up on the building that know how fast the wind's blowing all around the airport. But inside the hangars, with the door shut, you might not know. So before you open the door, it's good to know, what's the wind like outside. And I won't say where these are installed, but New Zealanders, if you feel like invading Australia, do it on a windy day when they'll be frightened to come outside. So we start with an Arduino brain, some communications modules, some really quite large light emitting diode numbers, and then we lash these up into an initial prototype. Now, the approach we took here is using some stuff called VeraBoard, which is just, if you've used a breadboard, which is essentially a bunch of little spring clips that are connected in rows, this is the solderable equivalent, where you've got a bunch of wires that run in one direction, and where you want to cut them, you just use a scalpel or a Stanley knife or even a drill bit. So our first prototype was put together using, I guess, 1960s technology. And we did actually decide to make our own circuit boards to allow us to connect the subsequent digits more comfortably. And this is another possibility for making your own circuit boards, which is using a computer-controlled milling machine to actually cut the circuit out of the copper. And once again, don't do it, because it's noisy, it's messy, it's relatively cheap. You can spend a couple $100 to get a machine that will do this for you. But again, it's a technology that's really past its use-by date. So I want to show you, as an example of that little small board I was cutting out there, the next level in computer-aided design tools. This is a tool called Eagle, which is now owned by Autodesk, who make AutoCAD and a number of other well-known tools. And it's free for small open source projects, and it's relatively cheap in the commercial realm, particularly compared to some of the incumbents in the business. So we start with our simple circuit diagram, which in this case is I've got 5 widely spaced pins on one of those big LED displays, and I want to convert it down to a closer together set of pins that fit the cable that I have. And this is the design that we came up with, and when I say we, it was actually John Oxer who convened the Open Hardware Mini-Conf yesterday, who did this design for me. But the idea we came up with was, let's not use a couple of little circuit boards here and there. Let's make one enormous circuit board that we put these big, and they're like this high, light displays on, which gives us everything together in one unit that we can put in a box and hang on the wall. And all it does is says, outside it's 120 kilometers an hour wind, don't go outside. And there we go, from something that we can send off to a printed circuit board manufacturer, get the result back in a few days. And all we have to do is take our collection of modules that we clip together with wires and instead poke them through the holes on this board, solder them on, and there's our project. And I keep one of these in my office, which I use as a number of days since the last time the first aid box was opened counter. Doesn't really need 3 digits, doesn't really need 2 digits, but there you go. So if you ever looked inside a phone or a computer these days, you'll see that the circuit boards don't have too many of those components with pins sticking through holes anymore. Instead, we use something called surface mount technology, which is scary initially when you look at it, but in practice, it actually turns out to be easier to use and simpler to use than the older technologies. In fact, I often ask my children and some of my interns who are high school aged kids to put these circuits together for me, and they find it not a challenge at all. So here's a project that's been kicking around in my head for 6 months or so, which is, let's build a robot that can make custom stickers for our laptops. And really, it's just a simple example of the kinds of thing that you can do with surface mount technology and some simple modules. And we began with, let's get an off-the-shelf compute module, some motor controllers, wire them all together on a breadboard, and just confirm that the motors that I found are going to work with this technology and that it's actually feasible to do what I wanted it to do. And from there we moved on to something that's a little more portable. This is again, an off-the-shelf component, an Arduino, a couple of motor controllers, some motors, a servo motor. And from there I went, okay, yes, this is going to work. Now I want to make it smaller. I want to make something that you can plop down on your laptop and have it draw directly onto your case. So we looked at how small can we get? So our target was a robot that can draw a 5 by 5 centimetre sticker. The robot itself is going to be no bigger than about 10 by 10 centimetres. So we made a circuit board that fits along one side of the robot. And it took us, again, a couple of goes to get it all working. We went through our different colours each time. We selected some switches, which on that red board there, actually clip into some holes that are drilled in the board. So again, we're using the circuit board to support our physical installation. And to put it all together, goes back to what I spoke about last year at LCA, which is 3D printing and rapid manufacturing. That's my intern Alice there, who was in grade 9 last year, who put that together and had an absolute blast doing it. And what we come up with at the end was this design. And again, we went through a number of iterations of that design, and we ended up being about twice as tall as I thought we would be. So instead of having a 10 by 4 centimetre board, I started thinking about, well, what if I made a circuit board that was the shape of that white end piece there? If it was about 10 centimetres long and maybe 6 or 8 centimetres high, but had some legs built into it. So now I want to talk about the kinds of things you can do with shaping your circuit board to suit your installation. And at the Brisbane Internet of Things meetup, which I'm helping to convene, we do the normal evening wine and nibblies and rabbiting on nights, but we also do a Saturday afternoon practical workshop where we build some things that are of interest to the membership. And for December, we decided to go with the Christmas theme, and I wanted to make some Christmas tree ornaments. And so I thought about some new flashing LED technology that had come to market, and I thought, oh, I reckon we can make something that allows us to sew these little LED sequins onto a quilt or onto a strip where they become a Christmas light strip. And so I designed this round circuit board that is sewable, and it's literally the simplest circuit you could possibly have. It's power goes in here and there, and the light flashes. It's not complicated at all. But I wanted to make a lot of them. So I designed one, and I sent it to the printed circuit board manufacturing house and said, I want 500 of these, what can you do? And they said, well, if we join them up into a panel and make them clippable, that won't be a problem. And so within a few days, I got back a sheaf of these little circuit boards, which we could break apart. And again, my wife and children helped in assembling those. And we got this year's project, which is the animated Christmas tree. That's a quilted fabric project that involves sewing on those little lights. And the design of those snowflakes got me thinking, well, maybe we should make an electronic snowflake to be the crowning part of that. So we designed a star, and we figured out how to get it cut out into that shape. We chucked some lights on there. And not being an electronics person, I didn't want to deal with having to build the computer, deal with communications. So I just made it accept an off-the-shelf compute module on the back. Again, it's the Lolland D1, cost about $3 to $4. And so with the two of those clipped together, we have a Christmas tree ornament that can do whatever you want it to do. You can program it to do various patterns. You can have it so your family can send you an email which changes your Christmas tree lights or whatever you want. And again, as not an engineer, I wanted to use this as an example of trying a different tool. I've used EagleCAD for a number of years, and that's well known in the hobbyist community as something that's fairly easy to learn. In the open source world, the go-to tool is called KiCad. It's not, I would say, as easy to learn. You would probably need to have a nerd on call to give you some tips initially. But I, with the help of one of my university interns, went from complete novice to sending this board off for manufacturer in the course of about 4 or 5 hours. So again, we start with our circuit diagram, which is I take an existing brain module and I simply downloaded the footprint for that off the internet. I've got some lights, I chuck them up there. And then I arrange those into the shape that I want, have the software wire it all up. And one of the handy things about KiCad is that it will give you a 3D visualization of what you've designed. So it can say, oh, it's going to look like this. And another of the important processes in the printed circuit board process is you've got your fiberglass baseboard, you've got your copper layers, and then you've got various layers of paint that go over the top. There's in this case, the green is actually an insulating paint, which helps you not get solder on the bits that you don't want to get solder on. So it makes it a lot easier for a novice to solder this board up, because the solder won't stick to the parts where it's not supposed to go. Whereas if you've built one of these boards in your tub of acid in the kitchen sink, or your little robot cutting machine in your garage, you don't get that benefit. And that's another reason why I think it's better simply to go to the commercial manufacturers these days. And so on top of your insulating paint layer, you get what's called a silkscreen layer, which is your explanatory text and assembly instructions. So in this case, I've got the name of the project, what all the connections are for, and so this gadget can not only light up the star at the top of the Christmas tree, I can use it to turn on all the extra lights around that installation in various combinations. So when you're going from that software from, okay, I've got a design, now I want to have it made, we're back to, unfortunately, the strange conservatism of the electronics world, in that there are no good open source file formats for exporting this. It's all de facto standard proprietary junk. But both EagleCAD and KiCad understand the proprietary junk formats. The main ones you'll encounter is a thing called Gerber format, which is the name of the originator, which describes where the copper gets cut away, where the silkscreen goes, where that masking layer goes, what the shape of the board is. So that's controlling essentially the robot that's going to go and build this board for you. And the second thing that you'll be outputting from your software is a description of where to drill the holes. And that's again in another weird proprietary format that nobody understands. But the good news is you don't really need to know any of this. You simply go, please plot my design. It'll spit out a bunch of gibberish. You chuck it in a zip file and upload it to your printed circuit board manufacturer. So for 10 of those boards, how much did it cost? $5. Not each, $5 for the lot. And if you don't really want to learn how to solder, or you don't know how to solder, or it frightens the bejesus out of you, then if you're prepared to wait a little longer, then a manufacturing house will assemble the whole thing for you and send you the finished product. How long does that take? For a normal thickness circuit board in the standard color, 3 to 4 days plus shipping time. So sending my design from here to the manufacturing house, 0 days. They'll have a look at it, tell you, yeah, that looks like it's going to work, or no, you've missed this, or that didn't work, or that's the wrong format. And so in a couple of hours, you'll have a go, no-go on your design. Then it goes through the process of etching and cutting and painting and then shipment back to you can take anywhere from 2 days to 2 weeks, depending on what option you choose. If you need it in a real hurry, there's places that will do this for you essentially next day. For not a lot more, you're talking $5 for the 1 week turnaround. If you really need it in 1 or 2 days, you might pay $50 for your 10 boards. But if you're in that situation, that's not a huge amount to pay. If you want different colors, if you want different thicknesses of boards, if you want flexible boards, other fancy stuff, you'll expect to take a little bit longer. It might go from 2 or 3 days up to a 5-day turnaround. And then if you want them to build it for you, that then requires them ordering the parts from somewhere, waiting for those parts to come, scheduling it into their manufacturing process. And that might take 3 to 4 weeks. It's not a huge amount of time. And certainly the convenience is hard to beat. So what do we get out of that? We got a Christmas project for the meetup that gives us a bunch of flashing lights and our Christmas quilt and a top piece, which is this star, which powers off of a USB board and animates into whatever patterns we like. And what I hope you can take away from this is that if you can join wires together to make flashy lights and such like with an Arduino, it's not actually very scary to go from there to something that is more robust, more reliable, able to be produced by the dozen or the 100 if you want to turn that into an Etsy project or something, which we're doing with this one. It's pretty simple, it's pretty cheap. The software is out there in several tiers, from really easy to use to quite sophisticated to insanely complex. You've got a huge amount of options in terms of colors and shapes and placements and things that you can put onto these circuit boards to augment your art project. And despite what you'd think, the production houses that are going to be building these designs for you are more than willing to help you as a novice get through the process. So I hope you found that helpful. I encourage you to go forth and create. If you're in Brisbane, I very much encourage you to come along to one of our workshops and give it a go. And that's it from me today, and I'm very happy to talk to you for the rest of the conference. And if you have any questions now, I'm more than happy to take those. Thank you.
Any questions? Right up there.
Thanks for the nice talk, Chris. I have a question regarding the versioning. You have experienced that you wanted to change things, so you redo things. You change the design. What are common faults that you have done that you have learned, so we don't do the same mistakes when you have done a mistake that is?
Can you speak up a little bit, please, Ruben? I can't quite hear you.
Ah, sorry. I was asking about the versioning. When you do more than one version, what are common things that you have experienced that are typical mistakes, so we may save doing those mistakes?
The typical problems we ran into were we didn't quite choose the right component. There might have been a couple of versions of the component with different pins. So it's good to take you've designed a circuit board, you've produced a design. Very, very worthwhile thing to do is to print it out on a laser printer or whatever and get all the parts that you're going to put on there and just place them where they're going to go, which gives you the chance to realize, oh wait, I got that one backwards, or there's two versions of that and one goes this way and one goes that way and I've used the wrong one. The other kind of problems we ran into were we missed connecting a wire that needed to be connected from here to there, and there's not a lot that you can do to help that. Some of the more expensive tools will actually simulate your circuit for you and tell you, yes, this is going to work. There are some great JavaScript tools for beginning people in electronics that will give you simple stuff like, I want to use a transistor to turn on a motor, and you can design that circuit in the web browser and it will tell you if it's going to work in terms of how many milliamps are going to flow to the motor, and is this transistor going to do what you think it's going to do. So as a beginner in electronics, there are some really helpful tools there. And I've linked to some of those in the slide deck. And I will, I've just thought of a few more I can throw on there as well, so I'll do that.
Anyone else?
What's the smallest run of circuit boards that you can ask for at one of these places without paying through the nose for it?
The standard package from the manufacturer that I use is 10 boards. They will do 5. It won't cost very much less. So I've done, I think the smallest order I've done is 5 of something. We made 10 of those big LED wind speed display boards, and the client wanted 8. So we ordered 10 boards thinking that would be plenty. We stuffed up 3 of them, so we ran out. In terms of soldering things on and then not quite getting it right and deciding to try and desolder it and then damaging the copper in the process. So we got 5 more. So yeah, the sweet spot is 10 boards. The volume discounts get quite good. So those little LED sequins, for 10 of them, it was going to turn out something like $1 each. Actually, sorry, 50 cents each. 10 boards for $5. And so I looked at the volume pricing and went, okay, how much would 100 cost me? How much would 200, 500? And once I got to 500, I was paying about 20 cents a board. So it was about 100 Australian dollars for 500 of those little sequins. And beyond that, I didn't see the unit price going down very much. So I locked down the $100, ordered 500 of them, and very, very happy with the outcome there.
You mentioned that you're going to put your slides online, so can you share with everybody, because I think there's a lot of us who we really want to go back through some of those links in detail and have a sort of longer or slower think about it. Can you share with us a URL to your website, or how we can, yeah, there we go.
So all my slides are on my personal website. So you'll find, for example, the presentation I did last year about 3D printing and laser cutting up there as well.
Does anyone else have a question?
So like you have another one behind you from Ruben.
Oh, you do another question.
When you are prototyping, I guess you don't want to ask 5 copies of something, right?
Mm-hmm.
So what's the best way to go when you have an idea? You want to make one PCB to see if it works, and then you will maybe make more copies. Is there any way, like maybe making 3 different versions and sending them to print?
If you just want to make one of something, the traditional ways have been to do the home etching with the acid, to do the milling with the computer. But we find that is actually cheaper and quicker and less hassle to just order 10 of the boards and hope we got it right and throw them out if it didn't. The other possibility is that you batch them together. Maybe you've got some other projects. Maybe you've got a hackerspace where there's other people working on projects. Is put 2 or 3 designs together into a single unit, send that off, and get it all done. The other good tip is that the particular service I use, which is called PCB Wave, the link's in the slides. If you put an order in, it will sit there in the cart, and if it hasn't shipped yet and you're going to do another order, you can simply ask them to combine the shipping on your existing order. So, particular with the starboard, I had an order in for something that was a client project. I got to the point where I needed to send this off for the meetup, and I simply piggybacked the shipping onto that existing order, so it didn't cost me anything extra. I just sent the order in, $5, 10 boards. That came the next week. So if you are in a situation where you've got collaborators, you've got people at a hackerspace, you're in a university where you've got students, you've got an art collective, then there's a lot of opportunities there to combine your projects and get even more economy out of your shipping agent. One more thing I want to mention is that absolutely talk to your local makerspace if you have one. I also operate a small incubator space where people can come in and use our tools and expertise. And I know there's maker spaces in most cities nowadays, so that's an excellent way to get more of this kind of tips of, oh, you should do this or try that, or how do you get your head around this software, which is not always super easy to use. There's a lot of opportunities there for learning your way into the process, and it's cheap enough that you can make a few mistakes along the way and still have fun.
All right, so let's give another big round of applause for Chris.